today is the sort of introduction to mass spectrometry, right where we left off last week after the introduction to liquid chromatography that I gave. And we're going to start with a really basic overview of how mass spectrometry works. Make sure that there we go. My mouse wasn't working. All right, so the very first thing that has to happen before a sample can be measured in a mass spectrometer is the sample needs to be ionized. So the only thing mass spectrometers can measure are ions. I'll explain this in more detail later. But if you have a sample coming from an LC column, or if you're directly injecting it, or if it's coming from a GC, doesn't really matter what the sample introduction method is. The samples need to be ionized. And then after that, the mass spectrometer actually sort of selects masses. That's one way to think of it. So there's some sort of protocol that you tell the mass spec to say, look at these masses and not those masses. And there's quite complex instructions you can give them. And you can think of a mass spectrometer almost as a filter, because it will select what you ask it to. And then there is an output signal, which a lot of people think the mass spectrometer is the detector, but in fact, the mass spectrometer is not the detector, although it incorporates a detector at the very end of the process. So there's something that actually measures ions as a sort of charge as it hits a detector plate at the very end. And that gives you converts that into an electronic signal. So we call the thing that does the ionizing the source. So the source will take your sample molecules and turn them into gaseous ions. The mass analyzer does the mass selection, and it does this by basically mass spectrometers move ions around. So the ions can be accelerated. They're in a vacuum. There's no other molecules in there that they can collide with. And by gently altering the voltages, the applied voltage in the system, you can make these ions move. And it's kind of cool. And then the detector measures the abundance of each ion, which tend to hit the detector all at once. So, if one ion hits the detector, you get a small signal. If 1,000 ions hit the detector, you get a much larger signal. And that's how we can quantify the number of ions we're measuring. Okay. I'm not sure why. Oh, yeah, we're going to start talking about ionization now in pretty deep depth. So, again, if it wasn't emphasized on the last slide, we need gaseous ions that the mass analyzer or mass filter is able to measure. This happens in the source, and there are basically two types of ionization techniques. The first is called hard ionization, and this is when high quantities of energy cause actual fragmentation of the molecule being ionized. And so then the resulting ions tend to be fragments of the original molecule, and they usually have a lower mass to charge ratio than the precursor mass or mass of the original molecule. Hard ionization techniques are really common with GCMS, and this was the original way that ionization happened up until the 80s and 90s. So what happens is you get a lot of energy and it breaks apart into ions. And it could be negative ions, but usually it's positive. So that's why I'm just using an example here. Soft ionization techniques impart less residual energy. And the idea here is to keep the precursor ion or molecule, intact. So for the most part, you should have the same or similar mass to charge as the regular molecule outside of the source. So here you're imparting a little less energy. I did that by making this yellow lightning bolt slightly less yellow. And then you keep your molecule intact. All right. So there are a few different types of hard ionization sources. The most commonly used is EI, or electron impact. This is when energetic electrons will interact with the solid or gas phase molecules to produce ions. And this is also one of the first ionization techniques, and it's still very popular. is very good for molecules with masses that are less than 600 Daltons, which is the same as an atomic mass unit. And also very good for gas phase separation. So EI is often used for gas chromatography. And so what this looks like is you have your precursor or parent molecule entering a beam of electrons, and those electrons are capable of breaking bonds and actually dissociating atoms and pieces off of the precursor. So you're usually knocking a couple of electrons out of outer shells and also breaking bonds. So when you break a bond, it's called a dissociative result. And if you don't break any bonds, that's a non-dissociative result. And usually the goal is to get here. There are very few of these non-ionized parent molecules, but almost always you actually get a mixture of these if you're using EI. So there'll be a small non-dissociative ionized parent molecules, which they often call the molecular ion, in your spectra, but it's small. And then you'll have a lot of fragments, which tend to be variable. The way this works, so that's sort of a theoretical diagram, but the way it actually works in design is that you've got usually a filament that releases the electrons into what's called a source block, and the sample is introduced into this block that has unapplied voltage as well. And there's a trap at the other end that usually has a magnet that draws the electrons through the source block. And as this is happening, it's pulling, of course, or causing these reactions. So knocking out the electrons and breaking bonds, and your sample will move through the source block and come out ionized. Another pretty commonly used hard ionization source that you may hear about, especially if you're working with metals, is inductively coupled plasma, or ICP. This is where the energy is supplied. The energy is supplied by electric currents, which are produced by electromagnetic induction. Typically, you're taking a gas like argon and turning it into plasma. And so there's this high temperature to make this happen, around 55 to 6,500 Kelvin. And it's comparable to that of the temperature that's reached at the surface or the photosphere of the sun. I used to work with ICP-MS. It's pretty fucking crazy to look at. Anyway, these torches. This atomizes the sample and creates atomic and small polyatomic molecules, which is why it's really good for measuring metal ions, for instance, in samples. So you could have a complex tissue sample and you want to measure how much mercury is in it. This is a great way to do that. All right. So what this ionization source looks like in practice is, when it kind of reminds me of like a sideways rotovap in its look, because there's a lot of glass inside of glass in these torches with this induction coil, although the induction coil is not the same as the like condensation coil but anyway, so for those of you who are chemists, this will make sense. For those of you who've never seen a rotovap, this won't make a lot of sense. But anyway, I'll start over. These are usually made of a very strong glass material, and your sample gets nebulized, where the sample gas is usually argon, and your liquid sample comes through, and the gas makes your sample turn into an aerosol. And some of that aerosol gets drawn in through a little bit of vacuum to what's called the torch. And then here's more argon going through, and there's an auxiliary argon that's heated, and then a coolant argon that's on the outside, sort of a sleeve in that glass torch. And then as the sample is sort of gaseous, getting heated up by the auxiliary argon and passing through the induction coil, a huge amount of energy goes through the sample in the induction coil, and it creates a plasma gas. So now your sample is mixed with this gaseous plasma argon, and then your sample goes through these cones that draw the pure ions into the mass spectrometer, and usually argon's going in too. So often you can get interferences from your gas, and there are a few other gases that are occasionally used in ICP if something you're measuring will completely overlap with like argon adducts or things like that. Anyway, we can talk about that another day. So what else have we got? We've got chemical ionization as a hard ionization technique. This is where the sample is introduced to a chamber that's filled with excess reagent gas, such as methane, and the reagent gas is more reactive. It becomes ionized with electrons, which forms these reactive species like CH5+, which then react with the sample to make what's called a pseudomolecular ion. So you're adding a hydrogen with an additional positive charge. The fragmentation of the sample is generally lower than that of EI, so it's a softer technique, even though it's still hard. And chemical ionization is actually pretty good for negative mode as well, but you have to use a different reagent gas. So it tends to work really well for halogenated molecules. So a lot of people who measure halogenated contaminants in samples tend to use chemical ionization. This is going to look a lot like electron impact ionization in its design, but you've got your reagent gas going into the sample block, and you then have a similar sort of filament with something that releases electrons and something that captures the electrons, and the electrons travel through your sample, and your reagent gas also travels at the same time, and this causes these pseudomolecular ions to be formed. And then those ions travel through into the mass analyzer. Another hard ionization technique is called atmospheric pressure chemical ionization, or APCI. It's very similar to chemical ionization. That's part of its name. So yes, good, that's intuitive, thank goodness. The sample here is delivered as a neutral spray, which is then ionized by a corona discharge needle, producing ions in a similar manner as chemical ionization. I've used APCI at my last, my job just before I came to Ontario Tech at the Ontario Ministry of Environment, Conservation and Parks. And again, I was using it to take liquid contaminant samples and ionize them to do GC TOF. It was really neat. Anyway, it's really well suited for low molecular weight nonpolar species that don't easily ionize with other techniques. It works well for liquid chromatography as well. So this one kind of looks a little bit like ICP-MS mixed with some of the concepts that you would have for chemical ionization, or chemical ionization. So you vaporize your sample with a hot neutral gas like nitrogen, and this gets your liquid sample into a gaseous vapor, and you're going to have both solvent and analyte molecules in that vapor. And then there's a needle here that releases a corona discharge at a relatively high voltage, 2,000 to 4,000 volts. And at this point in time, your analyte molecules should keep traveling, and your solvent gas should get ionized. And then you form similar sort of pseudomolecular ions with your not gas, but your gaseous solvent ions should now connect with your analyte molecules, which are difficult to ionize, creating this pseudomolecular ion, which then travels into the mass spec. Okay, so those are hard ionization sources. And I know this is kind of heavy, but I want everyone to know all of the potential ways that you can use ionization for different types of molecules. So now on to soft ionization. The biggest one here and the most common, and probably one of the most important, is electrospray ionization. We use this in our QTOF here at Ontario Tech. So what happens here, it's usually used with liquid chromatography. So you have a liquid droplet coming off the column and going into the source. And they're usually quite large. And that liquid will have a sort of charge applied to it by something similar to the corona discharge needle that I just showed you for APCI. And that applied voltage will give that liquid with the molecules in it either a positive or negative charge. You can do negative for ESI. And then you try to evaporate the liquid in that droplet as quickly as possible with a very hot neutral gas like nitrogen. And when you do that, the liquid, the water, evaporates out of the droplet really quickly. And the charge density of the molecules becomes increasingly high to the point where these charged molecules get so close together that they just can't handle it anymore. When they reach the final Rayleigh stability limit, because they're too close to each other, they want to repel each other, they literally sort of explode. And this is called a coulombic explosion, which creates ultimately gaseous ions. So there should be no longer any water or solvent at this point, and you actually have a proper molecular ion where your molecule is positively charged or negatively charged, and it's not necessarily because your solvent is stuck to it. What's really cool about electrospray ionization is that it works very well for large molecules and it leaves them intact. So if you have a peptide or a protein or perhaps an oligonucleotide that has multiple charges on it, the mass spec can capture it. So how does this work? So electrospray ionization has the ability to give multiple charges to a molecule. And usually the larger the molecule, the more charges it can hold. And so let's say the molecule of interest, which is in this example, is 10,000 Daltons. That's too big for most mass spectrometers. Most mass spectrometers can't go above like a 3,000 Dalton mass range. So they won't even see this. This would be too heavy. It's not even going to hit the detector. It's going to fall out of the mass filter. However, if you apply a charge of +2, the apparent mass to charge ratio becomes 5,001. And then as you apply more charges, the mass to charge ratio comes down and down, and it's literally division. So you divide it by 2, 3, 4, or 5, depending on whether you have one of those charge densities or charges on, or charge states is actually the technical term. Z is charge state. So the charge state on your molecule determines the apparent mass in the filter, or the mass to charge. This is great because it enabled us for the very first time to look at large molecules like proteins and oligonucleotides. And so it is this that actually changed the world in a big enough way that the guy who invented this, John Bennett Fenn, was awarded a Nobel Prize in 2002. So there is another soft ionization source I'm going to talk about, but we're talking about ESI right now. What are the advantages and disadvantages of ESI? Well, these soft ionization techniques allow for good tandem mass spectrometry. So I'm going to tell you more about tandem mass spectrometry a little later. But if you have your molecule intact, you can measure the intact mass, and then you can also cause that mass to fragment and measure with a second mass spectrometer the fragment ions, and that's called tandem mass spectrometry. You can't do that if your initial precursor molecule is already fragmented. At least you can't do it as well or reliably. As well, multiple charging allows for, as I just described, the ability to look at really large masses because the mass to charge ratio will cause an apparent reduction in mass for the filter to work with. You can couple this to liquid introduction methods like liquid chromatography, which also happens to be a really good technique for separating out biomolecules like oligonucleotides and proteins. And because of the way the sample solvent is vaporized, there is very little matrix interference or limitation on this method. So it's compatible with many types of mass analyzers and many different types of samples. The disadvantage is that when you have these multiple charges, it can result in very confusing mass spectra. It does not work well for non-volatile salts or buffers. If you have salts in your solvents, you often get what's called ion suppression. There are some things like ammonia buffers that can work all right, but you definitely don't want any sodium ions in your ESI source. It's not useful for very nonpolar compounds. If you've got very large nonpolar compounds, the best thing to do is to switch to GC and do something like CI or APCI. It's very destructive to the sample, so you can't recover your sample at the end, but that would be true for all mass spectrometry techniques. Okay. So other types of soft ionization sources are very similar to ESI in their concept of like making these multiply charged parent molecules and ions that aren't dissociated or fragmented, but they sort of work in different ways. So this one is called desorption electrospray ionization, or DESI. This is where you have a sample on a surface, and usually it's on sort of something similar to the stage of a microscope that can move around. And you basically bombard the surface with an electrospray source. So there's solvent and applied voltages and heat, and these electrospray droplets hit the surface and eject ions from the surface, the samples in the surface, and that goes into the mass spec. This isn't used very often, but it is pretty popular for people working in the polymer industry and surface coating. So it's used for that sort of thing. It's what people consider non-destructive because you only remove a few ions or molecules from the surface. And so it's probably really good for things like forensics or even possibly plant and animal tissues, because you could then go on and do staining and other types of analyses, visual analyses with your sample. Similar to DESI and likely more popular is matrix-assisted laser desorption ionization, or MALDI. And here you embed your sample in a special matrix. Oh, Simon. Okay, it's possible. Simon says that he thinks that they might have been using DESI for at airports for detection of explosives and things like that. And I think you might be right. I can't remember what they used there. But it is something that's very surface related, right? Sort of like a sniffer. Okay, and so back to MALDI. Your solvent is embedded in a special matrix, your sample is embedded in a matrix and on a special plate, and a laser beam, which is much higher energy than an electrospray, for instance, or fairly high energy, you can imagine, causes the matrix and the analyte to desorb properly from the plate. And then here you get that similar reaction that happens with APCI or CI, where the matrix transfers a proton to the analyte, and then the matrix sort of ends up getting dissolved and removed from the analyte, and then you have the pseudomolecular ion that travels to the mass analyzer. This is really good also for large molecules. A lot of people still use MALDI with proteins and other types of maybe oligos from gel to gel electrophoresis. So you could put a gel or you could excise bands from gels and then put them into this matrix and see how it works. You can also do imaging with high resolution mass spectrometers. So for those of you who don't know, here at the university, I'm working with a group of people to do a really large CFI proposal this year, and we're trying to bring in some new mass spectrometers, and not just to do proteomics like in my lab, but to do some really cool imaging with our forensic scientists, and this is something we're looking to do. So if we have our high resolution, I'm going to tell you about this mass spec later, but the IMS TOF, timsTOF, paired with one of these MALDIs, you can actually image at a molecular level. It's very hard to describe, but it's very cool. Okay, talk about it a little more later. So some concepts to be aware of that I've already sort of touched on that I'll just explain a little bit more for the idea of ionization sources and ionization of samples are two major concepts. There might be more on another slide, I can't remember, but okay. Starting with matrix effects. This is when there's a difference in the response or the way that the mass spec sees an analyte in standard solution versus the response for the same analyte in a biological matrix. So, if you put your analyte of interest, say you purchase a standard and you put it in pure solvent and you run it through the system, you'll get one signal. And often once that same standard or molecule is in something more complex like urine or saliva, you're going to see a change in the signal, even if you spike it in and you know exactly how much is supposed to be there and it's the same as your initial standard run, you're going to see a change in the ionization. So that's a matrix effect. It's caused by the combined effect of all the components in the sample other than the analyte. And, it can cause things like adduct formation or literally make the ionization process less efficient and therefore reduce the signal. If a specific component can be identified as causing an effect, then this is referred to as an interference. So, interfering ions can change the way the mass spec sees things. And if you know what it is, though, you can actually try to work with it. The worst is when you have a matrix effect that you just can't explain, which is probably what happens most often. We can also have ion suppression, which I mentioned as a matrix effect. It's a type of matrix effect that usually affects liquid chromatography mass spectrometry. So it doesn't really matter what kind of mass analyzer you're using. It has more to do with the ESI or the other type of ionization technique you're using. And this is just where you get reduced ionization. So in ESI, this happens a lot with sodium, like I mentioned before, but it can happen in APCI and a few other techniques as well, where you basically have competition for the energy that's traveling through the system to cause the ionization, and you end up ionizing these other interfering ions instead of your analyte of interest. So they sort of steal the electrons, so to speak. This usually occurs at the source. And like I said, it's really common with salts that are in buffers and or possibly other molecules that are in the sample that have different ionization energies, but they're more efficient. So if you have, say, a molecule of interest in urine, but there's three other, maybe it's a neurotransmitter or an amino acid you want to measure, but there's three other amino acids in there that are actually way better at ionizing and they have similar mass, they may swamp out the ionization for your analyte of interest. Okay, so ways to measure and correct for matrix effects. So first of all, if the matrix causes complete loss of good sensitivity, for instance, the analyte is at or below the detection limit, then you can do one of two things. The way I wrote that's kind of funny. You have to do one of two things. I might change that for future. I would say you can do one of two things, and I would have written one or two in the same numerical or word form. Anyhow, better sample preparation or cleanup to remove your interference in the matrix. So that's on the sample preparation side. You could do something like a solid phase extraction to remove the potential interferent, or do some sort of preparative chromatography, or you can try a different source. So for instance, APCI tends to be less prone to ion suppression than ESI. So maybe you just want to try a different source that can effectively ionize your interference and your analyte equally well. And then you just don't care. You can also compare a standard calibration curve in a pure solvent, as I sort of described at the beginning, to a calibration curve in the matrix. So you kind of make like a calibration curve in your, ideal circumstance with a standard, and then you spike that standard into a sample of urine that you expect to have very little of the thing you're looking for the moment or not, and you purposely spike it in with the same concentrations and then compare the two standard curves. And by comparing the slopes, you can actually correct if you want to. You can use the ratio as a correction factor. Another way to get around this is to include internal standards that are spiked into every sample. We can talk more about internal standards later, but and I know I go on about it, but in our lab, we often use stable isotope labeled standards that we can spike into our samples. And so this is the ideal. And here you should be, with any luck, your endogenous peak, or the molecule you want to measure in your sample versus the standard that you've spiked in should come out at the exact same retention time and should behave exactly the same in the mass spectrometer. And then you can simply correct for the suppression of your standard versus your endogenous, or use the suppression of your standard to correct for your endogenous, that is. So if the samples aren't exactly identical, but they behave very similarly, then you can also use this as a correction factor. This last one, the internal standard method, is considered the gold standard in analytical chemistry, but it's challenging if you don't necessarily know a lot about what's going on, why your sample's being suppressed, or if you can't get a standard that mimics your endogenous peak or is identical to it. So those other approaches will work as well. So let me summarize everything I've just explained to you guys, the different types of ionization sources. So electron impact ionization is applied really well to gas chromatography with volatile, thermally stable, and non-polar molecules. Inductively coupled plasma, or ICP, works very well for elemental analyses because it atomizes your sample. So you definitely don't want to try and measure molecules. You're generally measuring atoms. Chemical ionization, or CI, is excellent or very good at ionizing halogens. Atmospheric pressure CI is also very good at halogens, but as well, low molecular weight, non-polar species that aren't easily analyzed by other techniques. I said low molecular weight, but I wonder, when I say low, I mean relative, like lower than peptides and proteins. But I think you can still run like 500 Dalton samples through an APCI if you have like a large polyaromatic hydrocarbon, for instance. And then electrospray ionization, ESI, is excellent when it's paired with liquid chromatography, very good for compounds that are soluble in common solvents that do dissolve or vaporize really well in the ESI. So water, acetonitrile, methanol, and you get a wide range of molecular sizes. So you can ionize very large molecules like proteins and oligos. DESI is very good for intact samples that you might want to preserve and analyze in other ways. So things like surfaces or forensic samples, and also polymers. And matrix-assisted laser desorption ionization, or MALDI, is very good. It's very similar to DESI, but it works really well as well for larger biomolecules like proteins, oligonucleotides, and you can do imaging with it. So you could get some really cool two-dimensional data. And, so you could imagine having a sample perhaps of a special tumor and wanting to know what, proteins or things like that are present in this like slice of a tumor to figure out what's going on there. As I went through this table, I was showing you harder to softer ionization techniques.